Okay, electroplating. So as I was mentioning in the previous example, you connect a battery of higher voltage to a reaction that doesn't happen on its own. Basically, you have an electrolytic cell, and as long as you have a galvanic cell of greater voltage, you're gonna basically allow this non-spontaneous process to happen. You're basically doing work on it at the expense of your spontaneous galvanic cell. So typical electrolytic problem will ask you how much zinc is going to be deposited, right? And we know zinc is going to be deposited because that's the solid product that we're generating. How much of that can be deposited or recovered after 45 minutes of electrolysis, knowing that the current is 0.5 amps. So the first thing that we need to do here is to change the time to seconds. We're dealing with 45 minutes, and we know that for every minute we have 60 seconds. So that's the first conversion factor. Alright, the minutes cancel out. Now that you have seconds, you take and make use of the current. The current is 0.5 amps, but amps is the same thing as coulombs per second. So you input that as your current, and notice that seconds are on the opposite ends of the fraction so that they cancel out. And here is a very specific aspect of this process. Up until this conversion factor, all that we know is the total amount of charge that has been exchanged between the battery and the different electrodes. So what we do now is we use Faraday's constant, because we know that for every 96,485 coulombs worth of charge, we have exchanged 1 mole of electrons. And this is how we basically make the switch between charge ultimately to amount of electrons. And the amount of electrons comes into play when you think about the balance equation. So if you were to stop right here, this will tell you that you exchange a total of 0.0140 moles of electrons. So here's where you have to think about your equations. In particular, you want to think about your zinc reduction. Based on the half redox reaction of zinc, this is telling you that for every mole of zinc that you produced, you had to use up 2 moles of electrons. And so that becomes your conversion factor to follow, right? So you have 0.0140 total moles of electrons that were supplied, but for every 2 moles of electrons, you ended up producing 1 mole of zinc. And since we're looking for how much zinc we're going to produce, we're going to go all the way to mass, which means that we need to multiply the moles of zinc by the molar mass of zinc, which is 65.39 grams. And at this point, you'll find out that you collected a total of 0.0458 grams of zinc, or 45.8 milligrams. So, and by the way, you don't need to actually calculate the numerical value of the moles of electrons. You could have continued the conversion factor until you got to the grams of zinc and then done the entire thing in one go. But I kind of wanted to show you that when you have the moles of electrons, upon using Faraday's constant, you can then use the balanced number of electrons in your half redox reaction to figure out how many moles of electrons you're going to have for every mole of metal that you're dealing with. Okay, now one thing I'm going to mention right now, but this is going to be more important for the next lecture, is that when we do this type of reactions, typically we're doing this in water. And water, as you can see here, oxidizes to oxygen at 1.23 volts worth of potential, and at the same time, at a potential of 0, you start getting your water, right, your protons into hydrogen. So that's when water starts reducing. So this is the window of stability in terms of redox potentials, where you can add species to water without having water itself reacting. We're going to discuss that particular topic and analyze it in a little bit more detail in the next lecture. But for now, this concludes the second lecture on electrochemistry. I hope you liked it, and I'll see you in the next lecture series.